For portable applications, we're pleased to offer the CFT-810 audio fiber tracer and identifier. Using the same basic technology as the CFT-800, the CFT-810 is designed for fiber optic technicians who need a portable, battery-operated, easy-to-use instrument for tracing and identifying fiber optic patch cords and cables at the lowest possible cost. The CFT-810 has gained great acceptance around the world as an essential test instrument for network management and outside plant maintenance. Like the CFT-800, the CFT-810 operates over a single fiber, works with both single-mode and multi-mode fibers, and its wide dynamic range allows it to operate over spans of up to 30 kilometers with zero dead zone. It also works on the new generation of bend and sensitive fiber, something difficult or impossible to do with conventional visual fiber identifiers. These features make the CFT-810 extremely useful when troubleshooting and maintaining medium to large premises LANs, as well as metropolitan area networks. In these applications, tens or hundreds of patch cords, all of the same color, can be bundled together as they pass through central offices, equipment rooms, or cable management trays. In addition, these cables are often not labeled, making identification extremely difficult. Using the CFT-810, you can turn a specific fiber into a sensitive audio microphone, which can then be localized and identified by gently tapping or scratching on the cables. The sound is monitored through a headset or earphone connected to the instrument. Proper operation generally requires two technicians, one at the launch end of the fiber spans to be tested, and the other at the point where the cables must be identified. This could be along a cable tray in a premises network or in a manhole in the case of a metropolitan area network. However, if the point along the cable to be identified is physically very close to the instrument, then a single technician may be all that's needed. The CFT-810 functions like an interferometer, where a laser light source is split into two beams that travel around a loop and then return to an optical mixing module. The two coherent beams set up an interference pattern that is analyzed by the instrument's signal processing circuitry. At each end of the loop there is an optical splitter, one at the launch end to apply and sample the light from the loop, and the other at the remote end of the loop, which is connected to the fiber span to be tested. When a length of optical fiber is connected, the light carrying the interference pattern travels along the fiber and is reflected from the far end of the span back towards the source, which essentially lengthens the interferometer loop. Any physical disturbance to the fiber under test results in a change in the interference pattern, which is detected by the processing circuitry and converted to an audible signal. For proper operation, the instrument requires the end of the fiber under test to be highly reflective. When testing bare fibers, they should be cleaved to provide at least 4% reflection. With terminated cables, such as low reflection APC connectors and patch panels, additional reflection can be provided by using a short patch cord terminated at one end with the appropriate patch panel connector and a flat polished connector at the other end that is highly reflective. If there are connectors along the fiber span to be tested, it's important that their reflection be kept as small as possible. Otherwise, the instrument will only be able to see the cable span up to the first connector. To use the CFT-810, clean and connect a jumper between the optical port on the front panel of the instrument and the fiber span to be tested. The optical port is an APC-SC type connector, so depending on your network, you may need a hybrid jumper to mate with your panel connectors. If you're testing bare fibers, you can use an SC pigtail along with a temporary mechanical splice to make the connection. Connect an earphone or headset to the audio output jack on the front panel. Press the power button to switch the instrument on. The illuminated LCD display will indicate that the instrument is initializing and will then enter the standby mode. All functions of the instrument can be accessed by using the menu, select, and the up and down arrow keys. Before using the instrument for the first time, set the laser power output and operating wavelength. Press Menu and use the right arrow key until setup is displayed. Then press Select. The display will now show Output Power. Press Select again. You can now use the right and left arrow keys to cycle through the available power levels. The current power level of the instrument will be highlighted by an asterisk. In most cases, you'll want to use the highest output power. When you see the desired power level on the screen, press Select. The instrument will set your desired power level and return to the standby mode. After making settings, you may wish to save them so they'll be instantly available the next time the instrument is powered up. To do this, press the menu key, use the right arrow key to display Setup, and press Select. Press the right arrow key twice to display Save Settings, then press Select. Your settings will be saved and the instrument will return to the standby mode. We are now ready to begin making measurements. Start the laser by pressing the Run Stop key. The instrument will complete a 5-step configuration process, during which time it's important not to tap the cable or disturb the fiber optic jumper. When configuration is complete, the volume control knob is used to adjust the sound level in the headset as well as the sensitivity of the bar graph displayed on the screen. The second technician should be at the location where the target cable needs to be identified. It's recommended that this technician wear a hands-free headset while using the mobile phone, as both hands will be needed to make the test. The technician operating the instrument can now communicate with the remote technician over the cell phones. The remote technician now begins gently tapping the suspect cables in turn, while the instrument operator is listening for the loudest and clearest sound in the headset, as well as movement of the displayed bar graph. It's important to use the same amount of force when tapping each cable. A small force using a light tool like a pen or the handle of a small screwdriver works best. To prevent vibrations from passing between cables and giving false results, it's recommended that they be separated for a few meters along their length. If the cables are tied together, untie them and apply acoustic vibration pads where the test cable contacts other cables to reduce crosstalk. These pads are supplied with the instrument. Repeat this procedure on several cables until the target cable is positively identified. If the tapping sounds through the headset are too weak, the volume control can be increased or the sensitivity can be increased. The sensitivity can be toggled between low and high by pressing the right arrow key anytime during an active measurement. Keep in mind, however, that at higher sensitivities, more noise will be present on the signal. The front panel connector incorporates an automatic dust cover to prevent particles from entering the connector and to reduce the chance of laser radiation from entering the operator's eyes. The CFT-810 audio fiber tracer and identifier can easily identify cables in situations where the use of other identification technologies is impossible. With its zero dead zone, you can locate and trace cables from patch panel to patch panel up to 30 kilometers apart in either single mode or multi-mode systems. The instrument has other features and operating procedures that have not been presented in this video. Please consult your operator's guide for details. The CFT-810 will greatly reduce the time, effort, and expense in the organization, repair and maintenance of fiber optic cables, patch cords, and networks.